Okay, so we're going to get started with rotational kinematics. Actually, just in general, this half of the course is literally the first half of the course, except we're going to add rotational in front of all the words. So what do I mean by that? Well, we're going to start off with rotational kinematics. Then we're going to talk about rotational forces, which is what a torque is. A torque is just a rotational force. Then we're going to be talking about rotational energy, like rotational kinetic energy. We're going to be talking about rotational or angular momentum. Pretty much all of the topics we saw before in the first half of the year are coming back, and we're just throwing the word rotational in front of them, which means they're going to be a little bit harder. But if you did good on the stuff before then, or at least if you think you understand it now, like if you think you're good at kinematics now, or forces now, or energy now, there's a much better chance that you're going to succeed at this stuff. And if you don't know that stuff, well, if you don't know momentum, energy, and kinematics in the linear world, just the normal world, then you have no hope in the rotational world. So with that in mind, let's go ahead and get started. Before we go into the first question, I just want to quick give my 2 cents on rotational kinematics. I recommend pretty much anything I write down, you write down as well. So for rotational kinematics, if you remember linear kinematics, you would write down the 5 variables, or at least you had 5 variables: v initial, v final, acceleration, time, and delta x. And we would try and find as many of these variables as we could. And if we found 3 of them, then we could plug into one of the kinematic equations, and there were 4 kinematic equations. Now what we're going to be doing is we're going to be essentially doing the exact same thing, except these 5 variables right here are going to be replaced with omega initial, omega final, alpha, still time, and instead of delta x we have delta theta. Now just real quick to say what each of these is: omega initial is angular velocity, and that's initial angular velocity because it's omega initial. Omega final is just final angular velocity. Alpha is angular acceleration. Time is the exact same thing, it's just time. And then delta theta is going to be angular displacement. Which to you means how many times around a circle are we going, but the units need to be in radians, which we'll talk about today at length. Okay, any questions so far? So again, we are going to be using the kinematic equations, except their angular counterparts, which we'll discuss in just a couple minutes. So let's go ahead and jump into the first problem here. A helicopter's blades reach an angular speed of 400 RPM in 20 seconds. What is the angular acceleration? And then how many full rotations do the blades complete after 20 seconds? So for this problem, the first thing I'm going to do is I'm going to see how many of these variables I know. Omega initial, omega final, alpha, time, and delta theta. It doesn't say it in the problem. I probably should have mentioned it, but we're assuming we start from rest, which means angular velocity 0. Now, the final angular velocity, or angular speed, because remember, speed is just a velocity without a direction. In other words, we don't care about the plus or minus, which I'm just going to tell you, I don't care about the plus or minus right now for the next while. But it says 400 RPM. 400 RPM. In other words, I'm going to rewrite this as rotations per minute. Rotations per minute. We do not like rotations per minute in physics. We like units of radians and seconds. So in other words, I'm going to have to multiply 400 by some kind of combination of variables here to get me back to radians per second. So if I'm starting with 400 rotations per minute. Let's start with converting minutes, because that's actually easier. And I'm going to say in 1 minute there's 60 seconds. This is called dimensional analysis, where we pretty much cross off the units just like this. Minutes has to be in the numerator, and there's 60 seconds in the denominator. And then how do we go from rotations to radians? Well, whether it's rotations, revolutions, or just complete paths around a circle, I'm going to put 1 rotation in my denominator. And how many radians are in 1 rotation? How many radians are in a circle? The answer to that question is 2 pi. So we multiply by 2 pi radians over 1 rotation. Rotations will cancel out. We're going to be left now with radians per second. So now I'm just going to multiply this across in my calculator. It's 400 times 2 times pi divided by 60. We're going to get a final angular speed of 41.89, let's say. 41.89. And again, the units are radians per second. Now at this point, I also want to talk about what angular velocity is and what the difference between angular velocity and linear velocity is. So imagine my blades here of a helicopter. They're spinning around and around like this. Now, if I were to imagine the speed of these blades, there's two ways I could describe it. One is I could say how fast, what's the velocity of the blade itself. If I were to take a speed gun and say how fast are you going, that's one way we can measure the speed. The other way we can measure it is by saying, I'm going to draw a slightly different picture. We can also measure it by saying how fast do you cover this angle theta here. Well, theta is, in this case, I just drew an arbitrary line. Like theta can be anything. Theta can be 2 pi, theta can be whatever angle it is. But angular velocity is essentially saying how fast are you rotating? How fast are you rotating? And the reason why that distinction is important is because with velocity, I just have a question for you guys. Maybe you've been on a carousel before or something where you can go at different speeds depending on where you are in the thing, like a merry-go-round. If I'm closer to the center, then my velocity is going to be smaller. However, if I'm farther away from the center, well, then my velocity is going to be bigger. If you want the ultimate example of that in real life, think about the Earth going around the sun. The Earth is really going fast. Like, we can't feel it, but it's going thousands and thousands of miles per hour around the sun at any given point in time, like right now. And that's because it's so far away that the radius is so big that the velocity has to be that big in order to stay in orbit. So the further you are away, the higher your velocity is going to be. And we're not really going to use too much more outer space examples, but that's a good example for you right there. Now, let's finish up this question. We have 41.89 radians per second. I'm saying this is my omega final, my final angular velocity. Let me go back to this page. So omega final is 41.89. And again, the units are radians per second. Okay. Alpha, angular acceleration. That's what I'm actually asked to solve for, so I'll put a question mark there. Time, they tell us it's 20 seconds. And delta theta, how many full revolutions do the blades complete after 20 seconds? So there's two questions I'm being asked to solve for. First, I'm going to find alpha, then I'll find delta theta, which is the other part. So if I want to find alpha, notice I do have 3 of my 5 variables. 1, 2, 3. It means there is an equation I can plug into. Now, if this were linear motion, linear kinematics, I would say that equation is v final equals v initial plus acceleration times time. Except we don't have those variables here. We have their angular counterparts. In other words, we have omega final equals omega initial plus alpha times time. Did I lose anyone so far? Okay, good. So then omega final is going to be 41.89. That's equal to omega initial, which is 0, plus alpha, which is unknown, times a time of 20 seconds. So I can just plug this in my calculator, divide by 20. Alpha is going to be 41.89 divided by 20. It's going to be 2.09, and the units are radians per second squared. Okay, there we go. We found alpha. Now, how are we going to find delta theta, the number of revolutions? Well, remember, delta theta is actually measured in radians. Like, if I were to plug into a formula, I find delta theta, I'm going to find radians, I'm not going to find revolutions. That's a problem because the question's asking us to find revolutions. So how do I do that? Well, first, let's just find the number of radians, and then just like how we converted from revolutions per minute to radians per second, we're just going to go in the opposite direction. We're going to convert from radians to revolutions. So which equation should I plug into? I'll just tell you. It's going to be delta theta equals omega initial times time plus 1/2 alpha times squared. There's actually a couple correct equations at this point since we have pretty much all the variables, but this one will work for us since we just found alpha. So delta theta equals omega initial times time, which is 20. That won't matter because it's just times 0, plus 1/2 alpha. We just solved for it. It's 41.89, and then time squared is 20 squared. So all I need to do is plug this in a calculator. We're going to get delta theta 0.5 times 41.89 times 20 squared, we will get a final delta theta of 8,378. Again, the units are radians. It's not revolutions. In other words, this is not our final answer because I want to find revolutions. How do I convert this to revolutions? Well, as we did before, I'm going to multiply by something with a fraction bar here. In the denominator, I'm going to have radians. In the top, I'm going to have revolutions. And by the way, revolutions and rotations, I'm going to use them interchangeably because they are interchangeable. They mean the exact same thing. A rotation and a revolution is the exact same thing. And then I say to myself, in one revolution, there are 2 pi radians. That's the correct factor. So radians cancels. We're left with revolutions. I just need to divide my answer by 2 pi. So 8,378 divided by 2 divided by pi. And we are going to get a final answer of 1,333.4 revolutions. Now careful here, if you look back at the original question, I said, how many full revolutions do the blades complete after 20 seconds? In other words, full rotations, 1,333 revolutions. And that's the answer to the first one. For the person that joined late, don't worry about it. I'm recording this and uploading it to YouTube so you can check out this first question on your own. But any questions for this one? Great. Let's go on to the second one. It's going to be another rotational kinematics problem. A generator is rotating at 30 radians per second before it gets shut down and comes to a halt. It slows down with a constant angular acceleration of negative 7.5 radians per second, which, radians per second, that's just radians per second squared, really. And the fact that it's negative really just means that it's slowing down here. That's what the negative sign means. So then the question, how long until the generator comes to rest? And then the other part, how many revolutions does it complete? This time we can round to the nearest whole number. So it's going to be a very similar problem from before. I'm going to first write down my omega initial, omega final, alpha, time, and delta theta, and ask myself what I know. So this time, if I read the question, it was initially rotating at 30 radians per second. In other words, omega initial omega initial is going to be 30. Omega final, well, it says it's slowing down to a stop or a halt. So I know omega final is going to be 0. Alpha, they tell me it's negative 7.5 radians per second squared. I'll ignore the units right now. And we want to find time, and we want to find delta theta. Okay, great. So again, we have 3 of our 5 variables, which means we can plug in and solve for time, or delta theta. Let's start with time. It's actually going to be the exact same equation from before. Omega final equals omega initial plus alpha times time. Go ahead, I'll give you 30 seconds to solve this on your own. And then I'll be doing the work on the screen right now in the meantime. And hopefully you got the same answer as me, or if you didn't get it yet, you're probably close, hopefully. The time is going to be 4 seconds. So all you had to do was plug in the values here in the right spot, and then it was just algebra. Pretty straightforward. So time of 4 seconds for this first part. The second part of the question, how many revolutions does it complete? Round our answer to the nearest whole number. So again, we're going to be solving for delta theta, which is going to be in radians, and then we need to convert to revolutions. So I want to use a different equation than the one we used last time, just to show you different ones work. Let's use the equation that doesn't have time in it, which is omega final squared equals omega initial squared plus 2 alpha times delta theta. It's extremely similar to the one that we saw back at the beginning of the year, where we had v final squared equals v initial squared plus 2a delta x, except this time we're literally replacing all our variables with their rotational counterparts. So omega final, that's 0 squared, equals omega initial, 30 squared, plus 2 times alpha is negative 7.5, and delta theta is going to be what we're solving for here. Okay, so let's solve this. The left side's just 0, easy. 30 squared is 900, and then 2 times negative 7.5 is negative 15 delta theta. Add 15 delta theta to both sides, and then I can't do this in my head, but 900 divided by 15 will be 900 divided by 15. Still a round number. Great. 60, but not revolutions, radians. Now, how do we convert radians to revolutions? Exactly what we did before. We're either going to be multiplying by 2 pi or dividing by 2 pi. I want you to take 5 seconds on your own to think about that while I write this. So I'm saying radians is in the denominator, revolutions is in the numerator. In one revolution, there are 2 pi radians. We want to divide by 2 pi. So 60 divided by 2 divided by pi, that's going to give us 9.55. And again, the units are revolutions. This time they wanted us just to round to the nearest whole number, so I'm going to say 10 revolutions for this one. Any questions on this one? Now there is one more.
Yeah, I got.
Oh, go ahead.
Sorry, I got 94.24 for that.
Thank you, because you literally just pointed out the point I'm going to make right now. You have to be very careful when you plug this in your calculator, because if you put 60 divided by 2 pi, just like how I said it, your calculator is trying to multiply by pi. You need to put another division sign. So go ahead and try that and tell me if you get this answer.
Yeah, I got what you got now.
Yep, and that's the killer of these questions, is exactly that right there. So thank you for asking that question. That was a good question. Okay, and that's it for number 2. Number 3 is, I'm going to say, significantly more difficult. Let's talk about it. A bicyclist's tires increase in angular speed from 12 radians per second to 18 radians per second in a time of 5 seconds. They then maintain that speed for another 10 seconds. How many revolutions do the tires complete in the full 15 seconds? And then there's another part. If there's a piece of gum stuck to the edge of one of the tires and the tire's diameter is 0.7 meters, what is the tangential speed of the gum after 5 seconds? Okay, so we're going to break this up into 2 parts. The part with the piece of gum, that's a completely different topic that we haven't talked about yet, but we will in 5 minutes. Okay, so for this question, what I'm going to say is it starts out exactly the same. Omega initial, omega final, alpha, time, and delta theta. They even give us a lot of the information. It started at 12 radians per second, ended at 18 radians per second, and they set a time of 5 seconds. And then they're asking, actually there's another thing I need to mention here. They give 3 times. They give 5 seconds, 10 seconds, and 15 seconds. So it's really important to read this question carefully and understand that this part, this journey that the bicyclist is taking, can be split up into 2 parts. The part we're looking at right now is for the first 5 seconds, and then we're going to have to do another equation for the last 10 seconds. Then we're going to add the 2 answers together. That's how you get the full 15 seconds. So let's take it one step at a time now. At 5 seconds, so t equals 5, we are solving for delta theta. We don't even need to find alpha for this problem, it looks like. And luckily we do have an equation here that we can use to find delta theta. It is the following. Delta theta equals 1/2. That's supposed to be a 2. There we go. 1/2 times omega initial plus omega final divided by time. I'm sorry, times time. My bad. Times time. There we go. So it's this equation right here. Now let's go ahead and plug in everything we know. So delta theta equals 1/2 times omega initial is 12 plus omega final is 18 times a time of 5 seconds. We can just plug this in a calculator. 12 plus 18 is 30. 30 divided by 2 is 15. 15 times 5 is 75. And that's, again, radians. Now, we were asked to solve for revolutions, as is very common. Like, I'm not just doing that to be annoying. It's very common to ask for revolutions, not radians. So I just want us to get in the habit of doing that, because it's going to be so often that happens. So 75 radians. Again, I'm going to divide by 2 pi radians in the numerator. 1 revolution or 1 rotation. It's the exact same thing. So 75 divided by 2 divided by pi. We're going to get 11.9, and that's revolutions. I forget what I said, if we want to round or not, but it doesn't matter since this is only this is only half the answer anyway. To find the full answer, we need to know what's going on in the last 10 seconds. So I'm going to tell you for this, if you write down omega initial, omega final, alpha, time, and delta theta, and the only thing that changed is the time is now 10 seconds instead of 5, this is the wrong way of doing it. And let's talk about why that is. I'm going to scroll back up to the question. It says, we just read the first part for 5 seconds. Second part, they then maintain that speed for another 10 seconds. Question, what is the initial and final velocity for the bicyclist for the last 10 seconds? It's going to be 18 radians per second. It stays at 18, okay? And because of that, the angular acceleration is actually 0. Why is that important? It's important because if you do this method and you use the 5 variables, there's not a single equation that's going to work out for you because omega initial equals omega final and alpha is actually 0. I'm going to write that down. Alpha equals 0 because omega initial equals omega final, and they both equal 18 radians per second. If you try and plug this into any of your equations, you're just going to get a nonsensical answer. You can even try it on your own if you don't believe me. What I'm going to tell you, though, is we're going to use a different equation instead, and that equation is just very simple. It's omega, either the initial or the final, because they're both the same. Omega equals delta theta over time, and we can do this because it's constant speed. Constant speed, or constant angular speed in this case. And this was true back in kinematics when we were dealing with linear kinematics, and it's going to be true now as well. So this happens, I don't know how often it happens, but it's a good thing to know, definitely. We know omega, it's 18, delta theta is what we're solving for, and the time is 10. Very simple, delta theta is equal to 18 times 10, it's going to be 180, again, that's radians. So we do need to convert from radians to revolutions again. Let's do that here. 180 radians times 2 pi radians in the denominator, and then 1 revolution in the numerator. 180 divided by 2 divided by pi, we get 28.6, and that again is going to be revolutions. So I forget what we got for the other part. It was 11.9. So I'm going to add 11.9 plus 28.6, and that's going to give me the total number of revolutions. 11.9 plus 28.6. I got an answer of 40.5, and that's revolutions. I don't care what well, actually I should care. Let me go back to the question and actually see what I was asking, because it is important to actually check that. So it says, where is it? How many revolutions do the tires complete in the full 15 seconds? So how many revolutions? You could argue that since it says that it complete revolutions, that would only be 40. So personally, if I were a professor, I would accept both 40 and 40.5 because I don't think I'm very good with the wording in this question. But always read the questions carefully is the moral of the story there. And actually, we're not done with this problem yet because, as I said earlier, there is another part, and that is the following. If there is a piece of gum stuck to the edge of one of the tires, and the tire's diameter is 0.7 meters, what is the tangential speed of the gum after 5 seconds? So this involves another equation, and this equation is extremely, extremely important, especially on the final. And if there's, I don't know if you guys have one more midterm before the final, but it's going to be on it if you do have one. And that equation is the following. Tangential velocity, Vt, is equal to omega times the radius. In other words, I'm going to write out what each of these things says. Tangential velocity. What is tangential velocity? That's if you had the speed gun kind of velocity, okay? Is equal to omega, which is angular velocity, which is not like speed gun velocity. It's more like how fast are you rotating? Just how fast are you rotating? And then times the radius, which is r. And this equation right here is so important because it's never going to tell you explicitly that you need to know this equation. This equation you need to have in your back pocket ready to pull out at any moment, because if you don't, then you have no hope of answering this question. So let's go back to the question. If there is a piece of gum stuck to the edge of one of the tires and the tire's diameter is 0.7 meters, so right there they're telling us the radius. The radius is 0.7 divided by 2, which is 0.35 meters. And then it's asking what is the tangential speed of the gum after 5 seconds. So they're asking us to find VT, the tangential velocity. We know the radius, it's 0.35. And if we know omega, the angular velocity, then we're good. And good news, we do know the angular velocity at 5 seconds. I'll give you a few seconds to think about it. What is the angular velocity at 5 seconds? Well, at 5 seconds, that was the final in our first 5 seconds, if you think about it. So at 5 seconds, its angular speed is going to be 18 radians per second, which means times 18. The 0.35 times 18 is going to be our final answer. 0.35 times 18. We get 6.3, and the units are meters per second. Now, I do want to take a second to talk about units, because this almost makes no sense, and let's talk about why. So, velocity is meters per second. I'm just going to write the units right now. Velocity is meters per second, radius is measured in meters, and angular velocity is measured in radians per second. So technically, shouldn't it be meters times radians divided by seconds? In a way, yes, but more importantly, no, because radians is more of just a placeholder unit, and it also signifies circular motion. But here's the thing about tangential velocity. Tangential, even though we're moving in a circle, you don't have tangential velocity at any one point, because just look at this. Well, if I were to draw this line right here, angular velocity isn't a circular motion, right? Angular velocity is. But tangential velocity, no matter where I draw the tangential velocity, notice it's only pointing in one direction. And that's because velocity doesn't go in a circle. Velocity just points straight ahead. And it's constantly changing at every point in time, so that together the velocity moves in a circle, but at each individual point in time, it's not. It's a straight line. Kind of a weird concept to understand, but that's why velocity is meters per second and omega, angular velocity, is radians, because we're moving in a circle. Any questions on that? Okay. And that's going to do it for rotational kinematics. Now we're going to go on to the next topic, which is torque. So before we do the example problems here, I do want to give a little bit of a blurb, my opinion about torque, the equations that you need to know, and here they are. So first, it's good to know what the definition of torque is. Torque is going to be defined by force times distance, which is also the same as radius, times sine theta. Now here's the thing about sine theta, and I may have said the same thing about work when that equation was force times distance times cosine theta for work. I don't like sine theta. I'm actually going to cross out the sine theta here, or maybe even this entire equation. Instead, I'm going to say force perpendicular times distance, or force perpendicular times radius if you want to draw r instead. It's the exact same thing. Now, why did I do that? Well, it's because I don't always give you theta, the right angle, for sine. Sometimes it's cosine, sometimes it's sine. How do you know which one it is? Okay, let's talk about an example of torque, and it's the most classic example. Let's look at a door. So this is the hinge I'm drawing. This is my door. Again, here's the hinge over here, and this is a door. Okay, let's say the door swings out this way. Now my question to you is, if I have a force, think about this. If I have a force pointing up and to the right like this, and we see here we have two components, or at least we have an angle. We have a, let's say, 20-degree angle. The angle itself doesn't matter. But which component of force matters? I'll draw the different components. We have a force component going up like this in red, and we have a force component in blue going to the right. Think about this. Which component, the red or the blue, is actually causing this door to turn? In other words, if you only had the red force or the blue force, at least that direction, which one would get the door to move? If you pull a door in the red direction, you can even try it right now or after this lesson's over, that door ain't moving. You're like trying to pull the door off its hinge. It's just not going to happen. In order to make the door actually move, it's the blue force. It's perpendicular to your radius. And by the way, whenever I say F perpendicular, it's always perpendicular to the radius. And where's my radius? Right here. Or you could say distance D. And that is what we're talking about when I say F perpendicular. So in this example, I have the blue is F perpendicular, which then means the red is F parallel, and I'm going to just ignore it because I don't care about parallel. And then if I ask myself, what is F perpendicular? Well, I see it's the opposite leg of my angle, right? Like there's my angle, 20 degrees. This is a right triangle. F perpendicular is the opposite side. Oh, so in this case it was F sine theta times the distance. But again, I don't recommend memorizing sine. And is this easy? No, this is very difficult, but the only way you're going to get better is with practice. So definitely don't just blindly use sine. Actually think about it every time you look at this, because it is challenging and it really can mess you up. So with that in mind, we're going to look at a couple examples, and hopefully you start to get the hang of this. Oh, and one last thing, I do need to mention this. A lot of times we're going to be talking about net torque. Net torque. In other words, all of the torques added together going counterclockwise minus the torques going clockwise. We define counterclockwise as the positive motion, in case you're wondering why. It's a good question. I've wondered that myself for a while as well. But think about this. This counterclockwise notation, the arrow I just drew, is the exact same direction if you think of the unit circle. The unit circle also goes counterclockwise around your circle, starting at a 0-degree angle right there. So that's why counterclockwise is positive, clockwise is typically negative. If you want, though, I didn't tell you this, guys, don't get me in trouble. But if you want to, you can actually define clockwise as positive and counterclockwise as negative, as long as you're consistent, as long as you keep that notation the whole problem. And if you do that, you can get away with anything. Okay. So let's go ahead and look at a couple examples here. For the examples, I will be using counterclockwise as positive and clockwise as negative, just to follow suit with the equation. So here's the first one. I want to find what is the net torque on the wheel below. I see I have 3 torques here. The 30 Newton force. Remember, forces produce torques. So I have a 30 Newton force, a 50 Newton force, and a 100 Newton force like this. Let's deal with these forces one at a time, starting with the 30 Newton force, since that's the easiest. So again, torque is defined as force, the perpendicular component of force, times the distance. And now you may be wondering, well, that 30 newtons, is that the perpendicular component? I don't even see an angle. I'll tell you this. The answer is, it is perpendicular. Why? Because it's perpendicular to what? It's perpendicular to the radius. Here's my radius. Look at that. That forms a 90-degree angle, which is perpendicular. Okay? And the other reason why it's exactly perpendicular, because think about this. If I were to actually push this wheel, in the direction that this picture has, like to the left like this at the top, think about it. That's going to make the wheel spin. And that's exactly what we're talking about with torques. We're talking about forces that are causing things to spin or rotate. So for the first one, I'm going to say torque is equal to 30 newtons times my distance or radius, which in this case is 2 meters. And now, is it positive or negative? Is it a positive torque or a negative torque? Well, to answer that question, this 30 Newton force, is that in the clockwise direction or counterclockwise direction? If I were to kind of follow the arrow here, I see that it's continuing this way. It's causing the wheel to spin that way, which means the 30 Newton force is counterclockwise. So that's going to be positive. Does everyone see that? I know it's a confusing topic, but if anyone has any questions, please say it now. Okay, great. Now let's deal with the 100 Newton force, because that's the second easiest. So for this one, notice if you were to pull on the wheel in this direction, it's not going to spin. And the reason for that is if we were to draw a line from the center of the circle to that 100 Newton force, in other words, the radius or the distance, that radius is parallel with the 100 Newton force, not perpendicular. So for that reason, the 100 Newton force, that torque is just equal to 0. That torque is just equal to 0. Okay, good. Now for the last one, our 50 Newton force. So for the 50 Newton force, first of all, I'll just tell you it is perpendicular. Perpendicular to what? Perpendicular to the radius right there. There's our 90-degree angle. Perfect. And now I need to say that torque is equal to the force, which is 50, times the radius, which in this case, it's only located 1 meter away. It's not 2 meters. It's 1 meter away. So that brings up a good question. Does it matter where the force is located? Yes. It's the same reason. Why do they put doorknobs? Here's a serious question for you guys. Why do they put doorknobs on the opposite side of the hinge? They're not just doing that because it looks nice. It's because that gives you the maximum torque. If they put the doorknob in the middle of the in the middle of the door, you would have half the torque. You have to work twice as hard to open a door. It sounds obvious, it sounds intuitive, but there's physics behind it that explains everything. It's pretty cool. Unless you don't understand it, then it sucks. So it's 50 times 1, and is it positive or negative? Well, notice this 50 Newton force, if I kind of just draw an arrow in the direction of motion, it looks like it's causing the wheel to spin clockwise. We say clockwise is negative, so it's negative 50. So what does this mean? If I were to find my net torque, it's going to be 30 times 2, which is 60, plus 0, which we don't care about, and then minus the 50 torque. The answer is going to be 10, and what's the units for torque? It's going to be the Newton times meter. These are the units. You may be wondering, hey, Newton meters, isn't that the same thing as the joule? If you said that, you would be correct, and I'm surprised that you knew that. But it's not the joule, and specifically because joules it's just a different topic in physics. The units, yes, they happen to be the same, but we say Newton meters because torque is such a different topic than work and energy that we need new units because these two things do not mix very nicely. Any questions on that? Okay, great. Now there's one more torque problem we want to look at here. This one's, it just looks more complicated, so let's talk about it. What is the net torque on the wheel below? Let's start with the top one. It's the hardest. 5 newtons at a 30-degree angle like this. So once again, I don't know if it's sine or cosine just yet, but I do know this. If I were to draw my components, a red component going up and a blue component going to the right, and there's my right angle, this is a right triangle, the component I care about, is it the red or is it the blue? It's going to be the blue because that's the perpendicular. It's perpendicular to my radius, which means that that torque is going to be force 5 times distance. My radius, we see right here, it's 6, so 5 times 6, and then times, in this case, we see the angle is 30 degrees, and it's the opposite leg. F perpendicular is opposite the leg of the 30-degree angle, and opposite uses sine. So it will be sine of 30. Now, if I gave you that other angle, if I gave you this 60-degree angle right here, then it would be cosine of 60. Everyone see that? So it's not always sine. It really depends on what angle I give you. Now, you only need to choose one, so I'm going to erase the 60-degree angle, but it's good to know, just if you ever see that problem. Okay, and one last thing. This torque, this 5 Newton force, is that pushing in the clockwise or counterclockwise direction? Is it going to be positive or negative? Well, if I think about which way it's causing the wheel to spin, I kind of just draw my arrow in the direction of motion. That looks like clockwise, which means it's going to be negative. I'm going to simplify this. Torque equals negative 30 times sine of 30 is just 1/2. What a coincidence. That's going to be negative 15. Again, the units are Newton meter, but I'm going to worry about Newton meters at the very end of the problem anyway. Okay, so the next force, let's look at this 3 Newton force over here. Question, is this one exactly perpendicular to my radius? Yes, it is. Even though I kind of put it at a weird spot on the circle, if I draw my radius right there, I see I still have a right angle. That torque is super easy. It's just going to be torque equals 3, the force, times the radius, 6. And in this case, I don't even have sine of an angle because it's already perpendicular. We got the perpendicular component already. So if there's no angle, then it's either going to be just the full, like you don't even need to worry about the sine or cosine. It's just going to be 1 because sine of 0 degrees, sine of 90 is 1. If that's confusing to you, don't worry about it. Just worry about, is it parallel or perpendicular? Is there an angle in the first place? So this torque is just going to be 18. Oh, and one more thing, is that going to be positive or negative? So looking at this 3 Newton force, I see that just kind of following the direction of motion with this arrow here, which I'd like to draw the arrow every time because I think it's easier. We see that it's going to be counterclockwise, which we're defining as positive. So it will be positive 18 Newton meters for that torque. Then the final torque we have here is this 10 Newton force on the left. This one I think is pretty straightforward. It's going to be torque equals the force, 10 newtons, times that radius, which is only 4 meters this time. It's not the full 6, it's only 4. And then, do we have sine, cosine of some angle? Well, I don't have an angle. And I also see it's perpendicular. Again, perpendicular to my radius. Right there, there's a 90-degree angle, which means it's just going to, we don't have to worry about the angle. It's just 10 times 4. And then I have to ask myself, is that a positive or a negative? Well, again, following the direction of motion here, it's going to cause this wheel to spin clockwise, which means it's going to be negative. So negative 40 for the last torque. I add the three torques together. So net torque is equal to negative 15 plus 18 and then minus 40. We're going to get a final answer of negative 37 Newton meters. And there we go. Any questions on net torque? These problems are very fun. Yes. Anyone still writing? Okay. Next up we have rotational equilibrium. So rotational equilibrium, this is a very specific topic in torques, and it's actually one of the nicer topics I'm going to say. Why is that? So here's my notes on rotational equilibrium. It's literally as simple as this. The net torque is equal to 0. That's how you know we're dealing with a rotational equilibrium problem. The net torque is going to be 0. In other words, the torques going counterclockwise is equal to the torques going clockwise, and we already know the definition of torque. It's force perpendicular times the distance. So between these three equations, we can pretty much solve any rotational equilibrium problem. And how do you know it's rotational equilibrium? These things are going to be not rotating. Not rotating. They're held exactly in place. They're perfectly balanced. Okay, so let's look at the first one here. We want to find x given we have essentially a balance beam where we have a 2 kilogram mass on one side and 8 kilogram mass on the other. The one on the left is 34 centimeters and the other one is positioned x centimeters or meters away from the fulcrum of this lever. Now I do give you centimeters here, and I do that for two reasons. Number one, I want to make it hard for you guys, and number two, a lot of times in problems they actually do give you centimeters. So then the question becomes, well, do I need to convert to meters? And I'm going to tell you two answers. Yes, and you can also get away if you answer no. What do I mean by that? So first, let's find the answer if we use meters. I'm going to say 34 centimeters. We all know that's 0.34 meters, or at least hopefully you know that. You just divide by 100. And now let's find out what these torques are. So notice it's kind of hard to see here. Nothing's rotating, and we don't even have any forces yet. I'm going to tell you this. The force is gravity. The force is gravity. So notice here, I'm going to draw this in blue. For the 2 kilogram object, it's going to be mg going down. A mass of 2, g is 9.81. And then for the 8 kilogram object, I'll draw that in red. This vector is going down. Again, it's mg with a mass of 8, and g is still 9.81. Then you might be asking, well, hey, don't we have normal force acting on these objects as well? Yes, you would be correct. However, I'm not going to draw them because for the free body diagram here, I only care about the free body diagram for the bar itself. Like notice, I'm only drawing forces acting on the bar. And the reason I'm doing that is because for rotational equilibrium problems, we only care about the bar. I don't care about the masses themselves except for the fact that they have mass and they're causing a force of gravity downward on our bar. Hopefully that makes sense. If it doesn't, we're just going to do a couple examples today and hopefully it will start to make sense. So I'm going to say that this one on the left, these are my torques going, is that clockwise or counterclockwise rotation that this would be causing? This would be counterclockwise, and the 8 kilogram mass mg, that's kind of causing this motion to occur, which is going to be clockwise. So then if I say to myself the torques counterclockwise is equal to the torques going clockwise, the counterclockwise torque, that force, that 2 kilogram mass times g is 9.81, so that's the force, and again, torque is equal to force times distance. In this case, we don't even have any angles, right? So I'm not even going to worry about the perpendicular part, or the angle. So it's 2 times 9.81. What is the radius? The radius is going to be the distance from the pivot point. So the pivot point is located 0.34 meters away. 0.34, there we go. That's the left side. The right side, that's going to be 8 kilograms. So 8 is m times g is 9.81. And then that radius is x. That radius is just x. We're solving for x, right? So notice here, we pretty much have all the math. So I'm just going to say 2 times 9.81 times 0.34 on the left. That's going to give me 6.67 is equal to 8 times 9.81. That's going to be 78.48 on the right, or 78.48x. Then I just divide both sides by 78.48, and we'll get a final answer of x is 0.085. In other words, this is meters. And as I said earlier, you could have used centimeters for this problem. And it's okay. Like, normally we want to use meters, right? Because meters is what we use in physics. However, in this very specific problem, I'm just going to tell you it doesn't matter. For rotational static equilibrium problems like these, it doesn't matter if you use centimeters or meters if they give you centimeters to start with. If they give you meters to start with, you should use meters. If they give you centimeters to start with, you should use centimeters. And again, it's for these problems only. That's for these problems only. And by the way, if you did convert this to centimeters, you multiply it by 100, it would be 8.5 centimeters. This answer would be correct as well. Any questions here? So you all should be thinking one thing. You should have one question right now, and that is, for the clockwise portion, didn't I say that's negative? Like, shouldn't that be a negative sign right there? So that's a good question if you were to ask it. I'm going to tell you it doesn't matter because I kind of manipulated the equation so that I didn't have to worry about the negative. What do I mean by that? Well, remember, the original equation was torque counterclockwise minus torque clockwise is the net torque. And we're saying the net torque is 0. Why? Because it's not moving. So think of it this way. The torque itself is always positive. I repeat, the torque itself is always positive. The fact that it's negative came from the fact that it was in the clockwise direction. But notice if I add torque clockwise to both sides like this, the negative sign goes away now, and that's how we ended up with this equation. And I really like this equation for rotational static equilibrium because A, it works, B, it's simple, and C, I do the same thing every time, and it works every time. Okay, any questions on what I just said? Okay, cool. Now let's do one more example. This example is going to be significantly harder. I apologize. Not really. I mean, it's good preparing you for the hard ones. So number 2, find the normal force from the left and right sides. Okay, so this time I do care about the normal force, but I'm not talking about the normal force on this 10 kilogram box. Oh no. I'm talking about the normal force acting on my bar here. Because remember what I said in the last problem. I only care about the forces acting on the bar itself. So I'm going to draw blue for the left, normal force right there. Let's say NL. And then in red I'll say NR. And that's the normal force from the right side. Now other forces acting on this beam. I will have mg going down from the 10 kilogram mass, which is good. And now there's one more force I do need to consider. And it has to do with the fact that this time, unlike the last problem, this bar actually has a mass. And the reason why that matters is because gravity is going to be acting on this bar as well. So I actually need to draw gravity from the bar. I'll say capital mg because the bar is bigger. It's 100 kilograms. Now just real quick, I'm going to scroll up. And I want you to notice two things about this problem. Number 1, for this problem, the bar didn't have a mass, so I wouldn't include it anyway. Second, I tried to position the fulcrum. I probably should have made this more clear in the problem, but I tried to position the fulcrum exactly in the middle of the bar. Why is that important? Well, I'm going to scroll down again. So with any mass system, whether it's a long bar like this or just a normal package like the 10 kilogram mass there, we're going to treat it as a point source of mass at the center of the object. I repeat, we treat the force or the mass as if it were just at one point in the center of the object. What does that mean? It means that if I were to think, where is this mg located? It is located, if the whole beam is 3 meters long, it's located at the 1.5 meter mark. It's exactly halfway in the center of the bar. And that's important to know. Okay, great. So again, I'm going to set up the equation. Torques counterclockwise is equal to torques clockwise. And now we have a problem, I would say. If you were to do this equation, in every problem we've had so far, there was a clear pivot point. Like in the circle example, it was pivoted in the center. In the last balance beam problem, it was pivoted in the center. Like it was actually rotating about the center. We could see it clearly. Notice this one's not going to rotate at all. Like it's perfectly balanced on the left and right sides. There's no way it's going to rotate. Not a problem. It just means that we have the creative liberty of getting to choose the pivot point. So you can pick the pivot point on the left side. You can even choose the pivot point to be in the center right here. You can choose it to be on the right side. It doesn't matter. Now here's my advice to you. How many unknown variables do we have right now? I'm going to circle them. We don't know the left normal force. We don't know the right normal force. We have 2 unknown variables. So typically in math, 2 unknown variables means that we need 2 equations. However, I'm going to tell us we only need 1 equation if we pick the pivot point to be exactly on one of our either left or right normal force. So I'll choose the left just arbitrarily. It doesn't matter. So what am I saying here? I'm saying this is the pivot point. Choosing your pivot point is an art, just like any creative process. It takes practice to get really good at it. And normally the problem's pretty clear what they want you to be the pivot point. Like it'll either tell you or it's very obvious, like in the 2 examples we just saw before this. When it's not obvious, you need to pick it. And I always recommend picking it in the spot that will cancel out one of our variables. How will this cancel out a variable? Well, think about this. What's the torque on NL? Well, torque is equal to a force, so NL, times what's that radius? In other words, what's the distance from the normal force to the pivot point? It's on the pivot point. That distance is 0. That whole torque is 0. We actually just lose NL in the equation. That's actually fine at first because we need to get rid of it in order to solve for one of these things first. We're going to solve for NR first. Everyone okay with that? If you're lost, don't worry. I think it will make more sense in what I write next. So now we need to figure out what forces, what torques are going to be pointing counterclockwise. Remember, counterclockwise is this motion right here. And if I look at the forces, I see mg is going down and kind of in this clockwise shape. So mg is going to be clockwise. Capital Mg is also going to be clockwise because it's causing it to move that way. And the normal force on the right, that will follow the direction of counterclockwise. So I'm going to say normal force points on the counterclockwise side. So that torque is equal to a force, N sub r, times the distance. What's the distance from NR to my pivot point I chose? Notice it's the full 3 meters here. So NR times 3. I'm just going to tell you, don't worry about sine theta for this problem or cosine theta. There's no angles. Don't worry about it. Okay, now on the other side, I have lowercase mg, which is lowercase m is 10 kilograms. G is still 9.81. And that distance, what's the distance from the pivot point? It's kind of hard to see. It's kind of hidden. But I said it was 1 meter. That 10 kilogram mass is 1 meter away from the left side. So just times 1. Plus my torque from the 100 kilogram mass. That's going to be a mass of 100 times g, which is 9.81, times its distance, which is 1.5 meters. There we go. And it's 1.5 meters because, again, it's located exactly halfway in between. That center of mass is exactly halfway in between the bar. So now we have all our numbers. The only thing we don't know is NR. Let's go ahead and do some algebra and solve here. So on the left side, 3n sub r. On the right side, I just need to plug this in my calculator. 10 times 9.81 times 1 plus 100 times 9.81 times 1.5. We're going to get a final answer of, well, not final answer, 1569.6. Then divide that by 3 to find the normal force on the right side. Divide it by 3. We're going to get 523.2 newtons. There we go. We found the normal force on the right side. That's half the battle. Okay, now for the left side. What are we going to do? How are we going to find it? You have 2 options here. Number 1, you can say to yourself, oh, well, we picked the pivot point on the left here. What if we pick the pivot point on the right side now? Because then NR will go away. There's my new pivot point. And we're just going to do the exact same math to find NL. And you can do that, and that will work. And that's what I would recommend you do if you ever see this problem and you're not sure what to do. However, I'm going to tell you there's a much easier way to do it now that we know what NR is. So here's my question to you. We have rotational equilibrium. What does rotational equilibrium mean again? It's just a fancy word for not rotating. Here's my other question to you. We have translational static equilibrium here as well. You don't have to write that down. But translational static equilibrium means it's not just not rotating, it's also not moving. It's not moving up, down, left, or right. In other words, I can say my F net y is equal to 0. I repeat, F net, comma, y equals 0. What does that mean? It means all my forces pointing up is equal to my forces pointing down. This is Newton's second law back in the the linear, the translational world, the not rotational world. So I'm looking at all my forces pointing up. I have two. I have normal force on the left, normal force on the right. So normal force L and L plus normal force right we just solved for, 523.2. On the right side, the force is pointing down. Again, we have two of them, that mg and capital MG. So 10 times 9.81 plus 100 times 9.81. Notice with forces, I didn't have to factor in the radius, the distance at all. It doesn't matter for forces, which is pretty cool. And once again, I just need to solve the algebra here. So the right side, 10 times 9.81 plus 100 times 9.81. It is going to be a different number than before because I'm not factoring in the distance. So NL plus 523.2 on the right side, 1079.1. Subtract 523.2 from both sides, and we'll get a final answer of normal force on the left is 555.9 newtons. Okay, I'll give you a second to write that down. Okay, and now one more thing I want to mention. Notice normal force on the left is slightly higher than normal force on the right. Does that make sense? Should they be equal? I'm going to say no, they should not be equal. And just think about this in real life. See this 10 kilogram box here on the left side? Well, the left side should have a higher normal force because that 10 kilogram box is closer to the left side. So just from an intuition perspective, this makes sense. And again, the way we solved this question, we did two things. Number one, we said counterclockwise torques are equal to the clockwise torques, and that's because this thing's not rotating. Then once we found one of our sides, which we had to pick our pivot point, we chose the left side arbitrarily. We could have chosen the right side. It doesn't matter. Choosing the middle would be kind of tough because we'd have two unknown variables, and that would be annoying. But the left side is a good one to pick because we limit it down to one variable now. Once we found NR, the normal force on the right, again, we said F net is Y, and this is a pretty common problem whenever you see two unknown variables like this. So it doesn't happen all the time that you use this equation, but this is when you would use it. Okay. And that's it for torques. We're going to come back to torques in the very last question of the night, but any questions so far? So now the second to last topic we're going to be talking about today, moment of inertia. So moment of inertia is essentially describing how hard is it to rotate an object. So there's an equation for moment of inertia. There's actually many equations for moment of inertia. There is a table, and in general, the equation's this. I, which is moment of inertia, is equal to blank mr squared, where blank is a constant. There's a bunch of different moment of inertia constants, coefficients that you can have there. It can be 1, it can be 1/2, it can be 2/5, it can be 1/3, it can be 1/12. It all depends on what object you're looking at. There is a table that describes it. I don't have the table on me, but I'm going to be helping us out for the problems today when it comes to finding moment of inertia. Okay. So this is good. Now, there's one more thing I want to say about moment of inertia, and that is if you want to find the total moment of inertia, in other words, if you have multiple objects and you want to find the total, I total, the total moment of inertia is equal to I1 plus I2 plus ... however many objects you have. And we're going to be looking at an example today where you have two objects, and we're going to be adding the individual moments of inertia together to get the total. And one more thing, just in general, if you have a higher moment of inertia, a higher I value, it means that it's harder to rotate. Moment of inertia is all about how hard is it to rotate the thing. Okay, anyone still writing? So let's get into this question here. Number one, what is the moment of inertia for the dumbbell rotated about its center? So we see here we have a dumbbell, like 10 kilograms on each side, and we can assume that the bar is weightless, or else I would have included it. But the important thing is that the axis of rotation is in the center, and the whole thing is 1 meter long. So here's what I'm going to say for moment of inertia. I equals blank mr squared. Now for these objects, For these objects, we are going to consider them as point sources of mass. And that's important, and here's why. You don't have to write this down. You can just kind of watch this and take it in. There's a few different shapes we can have for a moment of inertia. One is we can have a hoop. The hoop is hollow everywhere except on the outside of the ring. I drew this dot in the center to recognize that that's the axis of rotation. It's the center. For a hoop, the equation is I equals mr squared. Again, you don't have to write this down. You can Google a table online, because no one except for me and maybe your professors actually know this, what most of the moments of inertia are. And you don't need to. You can actually, I would say, you pretty much have to use a table for most of these problems, or they have to tell you, because there's just so many to memorize and it's very annoying. Then you have the solid disk example. So the solid disk, imagine something like a tomato can or a bottle of water or something that's not hollow in the center. There's stuff inside of it. Disk. A frisbee would work as well. For this example, I is equal to 1/2 mr squared. Then there's a bunch of different shapes you can have here, but these are just two common ones. Now, notice for both of these, the axis of rotation is in the center. Everyone see that? The thing is rotating about its center. So I'm going to go back now to our problem. Notice this looks like it's in the shape of if it's a dumbbell, it could be like a cylinder shape, it could be a sphere. But the point is this: these dumbbells are not rotating about the center of the dumbbell. Oh no, they are rotating outside of the center of the dumbbell. Why is that important? Because that means they're point sources of mass. If it's a mass like this that's not touching the axis of rotation, it's a point source of mass. Why is that important? Because it means the moment of inertia is 1 mr squared. In other words, just mr squared. I'll erase the 1. But this is the equation for a point source of mass. Now again, if we want to find the total, we have to find I1 plus I2, the moment of inertia on the left plus the moment of inertia on the right. Luckily, this is symmetrical, so they will be equal. And we also know, well, I probably should have said this, it's exactly in the, I did say it's in the center. Great. So this distance is 1/2 meter. This distance is 1/2 or 0.5 meters, which means my individual moments of inertia, like I1, is going to be m, mass is 10, radius, which is the distance to the axis of rotation, so 1/2, and I'm not going to say m because that's just the units, so 1/2 squared, which is like 1/4, we're going to get 5/2 as our moment of inertia I1. Again, I2 is going to be the exact same thing because the mass is 10, distance is 1/2, you square it, you're going to get 5/2. I total is going to be 5/2 plus 5/2. We get a total moment of inertia of 5. And in case you're wondering what the units are, they are not pretty. It's going to be 5 kilogram meter per second. Wait, this isn't right. 5 kilogram meters squared. Yeah, these units are terrible. So I would say you don't have to memorize the units. Of course, maybe you do. But if you do, luckily there's a really easy way to remember it if you're good at units. And that is, remember, I is equal to something mr squared. Since this is just a coefficient, it could be 1/2, whatever. 1/2 doesn't have units. But mass has units of kilograms, radius has units of meters, and we're squaring it. That's how I always remember the units for moment of inertia. I just think of whatever mr squared. And the mr squared tells me what the units are. Again, I don't think you're going to have to know the units on the test, but if you do, it's not too bad to memorize. Okay, any questions on this one? We got 5 kilogram meters squared for the moment of inertia. Is that high? Well, let's compare it. Let's compare it to, what if we put the axis of rotation on the left side now? Let's compare these moment of inertia and see which one's bigger. In other words, which one's harder to rotate. You can even kind of think of it right now, you know? What do you think would be easier to rotate, when the axis of rotation is in the center like this, or when it's at one end? It's a good question. Let's answer it. So for this one, again, I total equals I1 plus I2. Since the axis of rotation is on top of my dumbbell, notice if I call this like I1 and the right side I2, I1, it's going to be a mass of 10 kilograms times a radius. That radius is 0 because it's touching the axis of rotation. Everyone see that? So R is 0 there. and you can square it. It's still going to be 0. In other words, I1 is just 0. Then we have I2. I2, again, the equation is mr squared, so 10 is the mass. The radius this time, it's not 1/2, it's the full 1 meter. So 1 squared, that's 10. We add these up together, we get I total is 10 kilogram meters squared. There's our answer. Notice when we put the thing hinged at the end point, it's double when it was hinged at the center. In other words, when things are hinged at the end, it's harder to move. And that's going to be pretty much true for just about any object in physics. Like, I can't think of an object that doesn't hold true. Okay. Any questions on that one? We're almost done. I think we just have 1 or 2 more questions to go. Yeah, so this is the last question of the night. Newton's second law of rotation. So first, let's talk about Newton's second law. Newton's second law said this, F equals ma, right? Well, we're going to have a torque equivalent of this equation. The equivalent for force is torque. The equivalent for mass is actually I, moment of inertia. And the equivalent for acceleration is alpha. Okay, so we have this new equation right here. Torque equals I times alpha. This is going to be very important. And it's exactly the same thing as when we had F equals ma. And another thing to note, this is not just F, in the same way this is not just torque. This is the net torque. Why is that important? Well, we're going to be combining 2 things now. Remember earlier when I said net torque is equal to all the torques going counterclockwise minus the torques going clockwise? Yeah, now we're going to set that equal to I times alpha. But the good news is, you know how in the last problem it took a while to find I, like we had to plug in this complicated thing? Well, normally they tell you I, or they tell you what the shape is, and then you can use that chart you can really Google a chart, moment of inertia chart or table, and you'll see for yourself what those coefficients are. But normally they tell you what the object is, and it's actually not that bad. Okay? So let's go ahead and look at an example with this stuff, because it's not exactly easy. What is the magnitude of the acceleration? I should have actually said angular acceleration for this one. I apologize. Angular acceleration. Okay. So again, the equation is going to be torque equals I times alpha, or I really should say net torque. Let's find the net torque first. And again, net torque has to do with things rotating. In this case, obviously, it's my wheel that's going to be rotating here. If I think about the forces acting on my wheel, on the left side, I have the force of gravity from a 12 kilogram object pulling it down. On the right side, I have another mg, force of gravity, pulling it down, but that one's only a mass of 6. If you can imagine this wheel's definitely going to be spinning counterclockwise. It just has to be. The 12 kilogram mass is bigger. It makes sense logically. And now we're going to prove it with physics. So the net torque is equal to, it's going to be a force times a distance. And remember, it's the perpendicular component, which I didn't give you angles for this one either, so don't worry about it. You don't have to worry about force perpendicular in most problems. The only time you have to worry about it for the most part is when they give you an angle, obviously. So let's do this. The 12 kilogram mass, that has a force mg. So force is mass 12, g is 9.81, right? And now that distance, think of it like this. Even though the mass is way down here, it's essentially coming into contact with the wheel at that point right there. There's where our force mg really is acting on the wheel. And that distance from the center is 1.5 meters. So times 1.5. I need more room. I'll write it down here. 12 times 9.81 times 1.5. That's all the torque from just the left side. And again, I'm going to say it's positive because that direction that I just drew right here is counterclockwise, which is good. And then minus the clockwise force or torque, that's going to be from the 6 kilogram mass. That torque is a mass of 6 times acceleration of gravity 9.81 times, well, there's no sine theta, so we don't need to worry about it. But we do need to worry about the distance, and that distance in the same way that it was 1.5 on the other side, it's going to be 1.5 right here. So times 1.5. Now I can just plug this in a calculator, and we'll find our net torque. It's not the final answer quite just yet, but we're almost there. 12 times 9.81 times 1.5 minus 6 times 9.81 times 1.5. We're going to get 88.29, and that's our net torque. And again, we're going to set this equal to I times alpha, and we're solving for alpha. So if I can find I, the moment of inertia, we're done, and we can go home. And actually, we're probably going to get done 15 minutes early today, which is great. So I, the moment of inertia, how do I find that? Well, in this case, I don't think I told you. I should have told you. That was my bad. I have it here in my notes. But it's a solid disk with mass 20 kilograms. The wheel is a solid disk with a mass of 20 kilograms. Why is that important? Well, for a solid disk, I is going to be 1/2 mr squared. Again, that would be found in a table. The coefficient is 1/2 for a solid disk. We know the mass is 20, so 1/2 times 20. And then we know r is 1.5, the radius, and we're going to square that. So we're going to get I equals 1/2 times 20 times 1.5 squared. We're going to get 22.5. I don't even care about the units for I, because I know the final answer is going to be in radians per second squared, right? Because that's what angular acceleration is. Yeah, these units are terrible, so I wouldn't worry too much about them in the middle steps, that is. So it's going to be 88.29 for torque. For I times alpha, it's 22.5 times alpha. We just need to divide both sides by 22.5. 88.29 divided by 22.5. We'll get a final answer for alpha of 3.92. And again, the units are radians per second squared. And also, since I was asking for magnitude of the acceleration, magnitude means even if I did get a negative answer here, I want to make it positive anyway. And again, that's because, look at the question, I said was the magnitude of the acceleration, of the angular acceleration, which means I don't care about the plus or minus. Okay, and that's pretty much going to wrap up today's lesson. Does anyone have any last